Since the dawn of consciousness, humanity has gazed upon the stars with a mixture of awe and longing. The vast expanse of space, with its countless stars and distant galaxies, has beckoned us to explore its mysteries. For centuries, our ancestors navigated by the stars, using their celestial patterns to chart courses across uncharted seas. With the advent of the space age, humanity's dream of reaching for the stars transformed into a tangible reality. We've walked on the moon, sent robotic emissaries to distant planets, and peered deep into the cosmos with powerful telescopes. Yet the challenges of interstellar travel, of journeying beyond our solar system to reach other star systems, remain daunting. The distances are immense, the timescales vast, and the dangers ever-present. Traditional spacecraft, reliant on finite fuel supplies and complex life support systems, are ill-suited for such arduous voyages. A paradigm shift in our approach to space travel is required, one that embraces innovative solutions and harnesses the power of nature itself. Enter the realm of anaerobic bacteria, microscopic organisms with the potential to revolutionize our approach to space exploration. These single-celled wonders, often overlooked in our macroscopic world, hold the key to overcoming some of the greatest obstacles to interstellar travel. The human body, a marvel of biological engineering, is remarkably ill-equipped for the harsh realities of deep space. We are creatures of Earth, finely tuned to thrive within the protective embrace of our planet's atmosphere and magnetic field. Venturing beyond this protective bubble exposes us to a multitude of threats. The vacuum of space, devoid of oxygen and atmospheric pressure, poses an immediate danger to human life. Prolonged exposure to microgravity leads to muscle atrophy, bone density loss, and cardiovascular problems. And then there's the ever-present threat of radiation, those high-energy particles that bombard our bodies from the depths of space. Cosmic rays and solar flares pose a significant risk to astronauts, increasing their chances of developing cancer and other radiation-related illnesses. Traditional spacecraft, while equipped with radiation shielding, can only provide limited protection, especially during extended missions. The challenges of providing food, water, and breathable air for astronauts on multi-year journeys represent a logistical nightmare. Carrying enough supplies for such extended voyages is impractical, requiring innovative solutions for resource management and recycling. In our quest to conquer the final frontier, we may find our greatest allies not in advanced technology, but in the microscopic organisms that have inhabited Earth for billions of years. Anaerobic bacteria, as their name suggests, thrive in environments devoid of oxygen, extracting energy from chemical reactions that do not require this life-sustaining gas. These remarkable organisms have evolved to survive in some of the most extreme environments on Earth, from deep ocean trenches to volcanic vents, demonstrating a resilience and adaptability that make them ideal candidates for space travel. Unlike humans, anaerobic bacteria are unfazed by the lack of oxygen in space. They are also remarkably resistant to radiation, thanks to their efficient DNA repair mechanisms. Moreover, these microscopic powerhouses can convert waste products into valuable resources, offering a sustainable solution for long-duration space missions. Perhaps the most critical challenge of space travel is providing a constant supply of breathable air for astronauts. Traditional spacecraft rely on oxygen tanks and chemical oxygen generators, both of which have limitations in terms of storage capacity and mission duration. Anaerobic bacteria, however, offer a more sustainable solution. While most anaerobic bacteria do not produce oxygen, certain species can generate it as a byproduct of their metabolic processes. By carefully selecting and cultivating these oxygen-producing bacteria, we can create bioreactors that continuously replenish the spacecraft's oxygen supply, eliminating the need for bulky tanks and complex chemical reactions. Imagine a spacecraft that breathes like a living organism, its air constantly refreshed by the activity of microscopic allies. Section 5. From Waste to Resource, the alchemy of anaerobic recycling. Waste management poses a significant challenge for long-duration space missions. Traditional spacecraft require efficient waste disposal systems, adding weight and complexity to their design. Anaerobic bacteria, with their remarkable ability to break down organic matter, offer a more elegant solution. These microbial alchemists can transform human waste, food scraps, and other organic materials into valuable resources, closing the loop on waste management and creating a more sustainable spacecraft ecosystem. Imagine a spacecraft where waste is not discarded but transformed into fertilizer for onboard plant growth, providing a source of fresh food and oxygen. Anaerobic digestion, the process by which these bacteria break down organic matter, also produces biogas, a mixture of methane and carbon dioxide that can be used as fuel or for other purposes. Section 6. Water of life. Quenching thirst in the cosmic desert. Water, the elixir of life, is a precious commodity in space. Transporting large quantities of water for extended missions is impractical, requiring innovative solutions for water recycling and purification. Anaerobic bacteria once again offer a promising solution. Certain species of anaerobic bacteria excel at water purification, removing harmful contaminants and pathogens from wastewater. By incorporating these bacteria into biofiltration systems, we can create closed-loop water recycling systems that continuously purify and replenish the spacecraft's water supply. Imagine a spacecraft where every drop of water is treated as a valuable resource, continuously recycled and reused, minimizing waste and ensuring the crew's hydration. Section 7. Shielding humanity, a microbial barrier against cosmic rays. Radiation exposure poses a significant threat to astronauts, increasing their risk of developing cancer and other health problems. Traditional spacecraft rely on physical shielding, such as lead or water tanks, to protect their crews from harmful cosmic rays. However, these shielding methods add significant weight to the spacecraft, limiting their payload capacity and maneuverability. Anaerobic bacteria, with their remarkable resistance to radiation, offer a potential solution to this challenge. By incorporating these radiation-resistant bacteria into the spacecraft structure, we can create a living shield that absorbs and deflects harmful radiation. Imagine a spacecraft with a living hull, its walls teeming with microscopic guardians, protecting its crew from the invisible dangers of space. Section 8. Ethical considerations. Navigating the moral labyrinth of bioengineering. The prospect of using genetically engineered bacteria in space travel raises important ethical considerations. Modifying the genetic makeup of organisms, even microscopic ones, carries potential risks and consequences that must be carefully considered. The release of genetically engineered bacteria into the environment, whether accidental or intentional, could have unforeseen ecological impacts. The potential for these bacteria to mutate or transfer their modified genes to other organisms raises concerns about unintended consequences. Furthermore, the use of genetically engineered organisms in space exploration raises questions about our responsibility to protect the integrity of extraterrestrial environments. It is crucial that we proceed with caution and develop strict guidelines and regulations to ensure the responsible use of this powerful technology. Section 9. A symbiotic future, humanity and bacteria united in exploration. The prospect of using anaerobic bacteria in space travel represents a paradigm shift in our approach to exploring the cosmos. By harnessing the power of these microscopic allies, we can overcome some of the greatest challenges of space travel and unlock new possibilities for human exploration. Imagine a future where spacecraft are not just metal boxes hurtling through space, but living ecosystems, their crews coexisting in a symbiotic relationship with their microbial companions. Anaerobic bacteria could provide a sustainable source of oxygen, recycle waste products, purify water, and even shield astronauts from harmful radiation. This symbiotic relationship could extend beyond the spacecraft itself. Genetically engineered bacteria could be deployed on other planets to terraform hostile environments, making them suitable for human habitation. They could be used to mine resources from asteroids and other celestial bodies, providing the raw materials for future space exploration. The journey to the stars is fraught with challenges, but it is a journey we are destined to take.